Okay, so we're going to look at whether a system of equations has one solution, many solutions, or no solution. So we'll start off with something. So what we're looking for is what variables or what values of h and k will give this one solution, many solutions, or no solutions. And we'll start off with a nice simple one. So if we look at this augmented matrix, all the augmented matrix is going to be is 1, 3, 2. 3HK. And we'll start with this simple one because we're going to look at it in terms of linear straight lines as well. So what we want to do is always just reduce this matrix as much as possible. So let's reduce this bottom row. So R2 is going to minus 3 lots of R1. That's what R2 is going to become. So we haven't touched the first row, so we can write that out 1, 3, 2. And it's going to be 3 minus 3 lots of this is 0, exactly what we want. R2 minus 3 lots of this is going to be H minus 9, and this is going to be K minus 3 lots of this is K minus 6. Now, what can happen, or what we want to happen, is if we have something like this, 1, 3, 2, 0, with a number here, and a number there, then everything's okay, and we'll get one unique solution to this problem. So if we get a number here and a number there, everything's fine. So as long as h is not 9, so if we want one solution or a unique solution, as long as h does not equal 9, we are going to get one solution to this equation. As long as h can be anything as long as it's not 9. So what happens if h is 9? So if h is 9, then what we're going to have here is we're going to have 9 minus 9. So if h is 9, we're going to have a 0 there, which is a problem. But if there is a 0 here as well, then it is fine. If h equals 9 and k equals 6, then that's okay, because if h equals 9 and k equals 6, this becomes 1, 3, 2, 0, 0, 0. And that's fine. It just means because we've got two unknowns and really only one equation, this is going to give infinite solutions. So we get one solution if h equals 9. Sorry, if h doesn't equal 9. If h equals 9 and k equals 6, that's infinite solutions. What happens if there's no solution? Well, if h equals 9, if h equals 9 and k does not equal 6, let's say k equals 5, what we'll get here suddenly, h equals 9, so we get a 0 here. But if k equaled 5, 5 minus 6 is minus 1. See, it's okay if there's zeros along here. 0 times x plus 0 times y equals 0. Fine. This is saying 0 times x plus 0 times y gives us minus 1. That can't happen. So this is no solutions. Okay, so if h equals 9 and k equals something other than 6, there are no solutions. So let's go back to our little equations. And we could have guessed that from the start. Here, if we've got x plus 3y equals 2, if we've got h equaling 9 and k equaling 6, what we really have is x plus 3y equals 2, and we have 3x plus 9y equals 6. And obviously, these two equations are exactly the same equation. This one's just been multiplied by 3. So if we graphed it, and I'm not going to graph it properly, let's say that is x plus 3y equals 2, then this is 3x plus 9y equals 6. So really what you've got is exactly the same graph, and that is obviously going to give us infinite solutions. So if H equals 9, K equals 6, infinite solutions, which is exactly what we got here. If H equals 9, K equals 6, infinite solutions. Suppose you've got, if H equals 9 and K doesn't equal 6, in other words, if this equals 10, what we've really done is we've drawn parallel lines. So one is x plus 3y equals 2. This is really x plus 3y equals 10 over 3. So you get these parallel lines, and that's why you get no solutions. What happens when the h doesn't equal 9? If the h doesn't equal 9 back here, what you basically get is that this could be 8. And straight away, if you look at 3x plus 8y, and we look back at our, suddenly you haven't got parallel lines, and as soon as you get non-parallel lines, they might only be missing by a bit, but that's when you are going to get one solution. So in summary, if you get a matrix that looks like this, 1, 0, 0, even if it's 5, 6, 0, 0, minus 2, and some numbers here, 1, 7, 2, like that, that is going to be one solution. That's one solution. If you have something like this, you get 1, 0, 0, 0, 5, 6, 0, 0, 0. Two things can happen in this case. If this is 3, 1, 0, that's fine, because this line still makes sense. But what we have is 2 equations and 3 unknowns. So what we've got in that situation is an infinite amount of solutions. Infinite, no, it's nice if you spell it right. Infinite solutions. So how do you get no solutions? The way you get no solutions is you have the same sort of thing happening. You have 1, 3, 2, 6, 0, 3, 7, 2. And this bottom one is 0, 0, 0, but it's 7, or a 2, or a 6, or a minus 1. 0 plus 0 plus 0 can't equal 7. So this is when no solutions happen.
Really?
Okay? Because there are no solutions to that. So let's look at a more difficult one, perhaps. What values of k will give you the 3 different cases in this one? So first thing we're going to do is set up an augmented matrix. So it's 1, 1, k, 2, 3, 4, 2k, 2, 3, minus 1, 1. So there's our augmented matrix. And just because the k's are there, it's not going to change anything. What we want is zeros underneath here. So let's try to get rid of this. So row 2 is going to be row 2 minus 3 lots of row 1. So we're not going to touch this top row. So row 2 minus 3 lots of that is 0. 4 minus 3 lots of that is going to be 4 minus 3. 2 minus 3 lots of that is going to be 2 minus k. K minus 3 lots of that is going to be k minus 6. And what's the last one going to be? It's pretty much the same. It's going to be row 3 minus 2 lots of row 1. So I've kept it fairly simple, but 2 minus 2 lots of that is 0. 3 minus 2 lots of that is 1. Minus 1 minus 2 lots of that is minus 1 minus 2k. And 1 minus 2 lots of 2 is going to be 3, minus 3, sorry. Okay. And so we've got some 1s here, which is nice. And we just want to make this a 0. Then it will be in row echelon form. It doesn't look nice because the k's, but that's okay. We can deal with that. So row 3